back now for the last part for today. All right, now, if we have time at the end of the year, we'll go into a much greater detail about why all this stuff works. But your chapter 14 dives a little bit into radioactivity. Okay, radioactivity is whenever the elements, for whatever reason, fall apart. Okay, literally. Okay, so we talked about how you can have carbon 12, carbon 13, and carbon 14. Your protons and your neutrons inside the nucleus are held together by something called a strong force. All right, that's literally the name of it. It is the strongest force in nature. Gravity is actually the weakest force in nature. And if they get too big, like carbon 14, it just happens to be a little bit too big and it just can't hold on. Carbon 13 and carbon 14, or carbon 13, sorry, 12 and 13, can stay together forever. Their strong force can hold on forever. But carbon 14 just gets a little too fat. All right. And so they become what we call unstable, which means the strong force just cannot hold on to them at all. Okay. I usually liken this to somebody falls off a cliff. I can hold on to one of you with one arm. Somebody else falls off a cliff. I can hold on to another with another arm. But if a third person jumps on, I can't. And so eventually I'm going to have to let go. And that's exactly what happens. When that lets go, when the strong force inside lets go, it's called nuclear decay or radioactivity. Sorry. Okay. That's all it is. Simply falling apart from the strong force. All right. When that happens, okay, so there's a little breakdown of all that kind of stuff. Again, breaks down just because it's too big. All right. Every element after 83, however, is so big that all of the isotopes fall apart. All right. It just doesn't happen that way or whatever. And again, I'm trying to zip through this as fast as I can. When that happens, one of four things happen. Okay. Your book on page 320 has a really good picture of alpha and beta decay. But I just want to go through this with you. Alpha, which is this little Greek fish right here, all right, says to emit a helium. But really what it emits is two protons and two neutrons. So you took this atom and it fell apart. And when I say emit, it means it lets go of two protons and two neutrons. Now, because of that, the mass changes and the element changes because it lost two protons. Now remember, this is not what we're doing. This is just something that we discovered happens in nature. Sometimes it deposits, it's too big, too fat, shakes apart, and falls apart. Okay. In beta, all right, in beta decay, what ends up happening is you lose an electron from this whole mess. This whole reaction happened to this. And what ends up happening is the mass number stays the same, but we also gain a proton in here as well. And again, look at page 320 on your book, all right, and it shows you protons increase by one, all that kind of stuff. And again, if we change the proton, we change the element. Gamma is the one you guys probably all know about before because this is the green one. This is what made the Hulk and all that other kind of stuff in your Avenger movies and things like that. Gamma has no mass whatsoever. All right, it just loses energy as light. And so, again, it's a shakeup of this element, and then some gamma rays are given off. All right, if you ever heard of Marie Curie, that's kind of how this works out. If you wonder where these notes are, these are in your nuclear decay notes at the very end, because this is what I covered at the very end, but your chapter covers it right now. And because of the time constraints, I'm not sure I'm ever going to get back to this, so we're just going to cover this today. And then the last one is neutron emission. Now, that's not really mentioned in your book at all. They just mentioned alpha, beta, and gamma. All right, but that just means you lose a neutron. Now, from 1 to 4, for these four things, okay, this is very mild and very weak. All right, this can literally be stopped by a piece of paper. Beta decay can be stopped by a shirt. So, I mean, you're okay if you go with that kind of stuff. Gamma rays, that causes a little bit more damage, and neutron emission is the one you want to get for making sure everything's okay. All right. So I just want to show you some basic stuff here. Now, again, if we do have time at the end of the trimester, we'll go into much greater detail with all of these. So why do we do this right now? Because these go with those isotopes things. All right. So in carbon has an isotope carbon 12, which is fine. An isotope carbon 13, which is fine. But a heavy isotope called carbon 14, all right, that falls apart. And we want to know what happens when it falls apart. Okay, we talked about carbon 12, carbon 13, carbon 14. Carbon 14 goes through beta emission. All right, and so beta emission, it loses an electron, gains a proton, all these other kind of things happen. It's a really weird sort of reaction, but it ends up for this one for carbon 14 actually ends up turning into nitrogen 14, which is a stable, perfect atom, but it gives off a little radiation as it does it. Okay, so look at your chart on page 320 in your book. All right, about alpha and beta decay, and that should hope you explain a little bit. Again, we'll go into much greater detail later on. I just want you to know what radioactivity is. It's simply when the atoms are a little too big to handle what they do. All right, and so they have to break apart just a little bit. Okay, all right, have a great day. Thanks.